If you're watching this video, you've probably heard that throwing a penny off the Empire State Building could kill someone below on the street. And if you've seen part 1 of this series, then you already know the answer to that. Spoiler alert, it won't kill anyone. It will honestly feel like a flick to the head. But now you might be wondering what things could kill someone if thrown from such a height. In this video, we'll mathematically throw many objects off the Empire State Building to see just how deadly they are. Welcome back to Math the World. Before we go chucking objects off the Empire State Building, we do need to recap a few important concepts from part 1 of this series. In part 1, we needed to determine how much blunt impact force was needed for a fatality. We analyzed 2 real-world situations where someone died, a baseball player getting hit in the head by an 85-mile-an-hour pitch, and a gloveless boxer punching the back of someone's head in a pub. These events gave us a rough range of 3,700 to 5,500 newtons of average impact force required for death to occur from a blunt object hitting someone in the head. And we used this equation to calculate the average impact force and doubled it to get peak impact force as well. The other important concept was terminal velocity. We determined that a penny reaches its terminal velocity well before hitting the ground if thrown from the Empire State Building. In fact, it will reach terminal velocity in as little as 15 meters. This means that no matter how much further it falls after 15 meters, it will maintain the same speed for the rest of the fall. To determine the terminal velocity of an object, we used this equation. Both of these equations will be important as we decide how deadly the objects are that we'll be throwing off the Empire State Building today. We'll mathematically throw a cell phone, a mug, a baseball, a book, a tape measure, and a watermelon from the roof of the Empire State Building and see how lethal these objects are. All of these objects are relatively small and light. Given that a skydiver reaches terminal velocity in about 1,500 feet, let's assume all of these objects will reach their terminal velocity before hitting the ground, after falling just 1,250 feet from the Empire State Building roof. Let's start with the cell phone. To find impact force, we need mass, velocity, and contact time. The new iPhone 15 has a mass of 0.171 kilograms. It's also rather hard, so let's assume contact time is similar to our baseball from part 1, 0.001 seconds. Lastly, we'll need to find its terminal velocity. We know mass, gravity, and air density, but we need to find cross-sectional area and drag coefficient. Area will be quick. A phone will likely tumble as it falls because of the large surface area of the face. To estimate the cross-sectional area, let's find the area of the face of the phone and the small edges of the phone and do an average. Given these dimensions from the Apple website, we can quickly calculate that the average cross-sectional area is 0.00409 meters squared. Now we need a drag coefficient. Our penny falling on its face had a drag coefficient of 1.17, and falling on its edge we estimated at 0.4. Since our phone is tumbling and has a similar thin plate shape, let's average these two and use 0.8 for our drag coefficient. This gives us a terminal velocity of about 28 meters per second, which is 62 miles per hour. A decent speed. Now we can plug that into our impact force equation, and we get 4,811 newtons on average and a peak of 9,622 newtons. This is definitely within our range of being lethal and could do some serious damage. For our other objects, we won't go into detail for all of the assumptions, but here are the values we estimated and our final calculations. For each of them, we used a similar process to the phone. We assumed the objects were tumbling and averaged cross-sectional areas of the objects as well as averaging drag coefficients. As you can see, most of these are quite lethal, all except the tape measure, though that still would not be fun to get hit in the head with. This is why hard helmets are so important at construction sites. I will also specify that the book we had in mind was a hardbound copy of the 7th Harry Potter book, taped shut so it's not flopping around while falling. This one is extremely dangerous, so please do not go throwing books off of buildings. Finally, I want to get a little more into that watermelon situation. You may be familiar with this clip from the Amazing Race TV show. And you may be wondering, how did she not die? Really, a watermelon can easily weigh 10 pounds, and that could easily have been going 30 miles an hour or more. Let's do an analysis and run some numbers. From this video footage, we can actually estimate all the things we need to find impact force. This footage was shot at 30 frames per second. I estimated that the distance from her face to the center of the catapult is about 10 feet. The watermelon covers this distance in 6 frames, which is about 0.2 seconds. This means that the watermelon's traveling about 50 feet per second, or about 15 meters per second when it collides with her face. We can also estimate the contact time duration. The watermelon appears to stay in contact for 3 frames, which would be about 0.1 seconds. Lastly, we need the mass of the watermelon. Looking at this clip here, these watermelons look smaller than average, which is what we used when we threw our watermelon mathematically off the Empire State Building. I'd guess these are about 10 inches long, so probably more like 6 kilograms in mass, or around 13 pounds. Putting this all together, we get an impact force of just 900 newtons. Not within our range of death, but probably a good concussion, which is all she walked away with. This watermelon scenario actually points out a really important part of our impact force equation: contact time duration. If our watermelon behaved more like our baseball and remained in contact for only 0.001 seconds, we quickly go from 900 newtons to 90,000 newtons, a huge difference. This is why hard and soft objects make such a huge difference in these situations. Soft objects lengthen the contact time, dissipating the amount of energy being experienced over a longer amount of time and lower the average and peak impact force. This makes surviving these impacts much more likely, and this is why boxers wear gloves, gymnasts tumble on mats, batting helmets have foam pads, and cars have built-in crumple zones. So hopefully this video has shown you that throwing objects off tall buildings can have major consequences. So please, don't be an idiot. Let's keep everyone safe. Thank you for watching. Please subscribe and share our videos. Be sure to follow Math the World on Twitter, Instagram, and Facebook. Thank you so much for your support.